Susie,
Rob.
so this week we're talking about amniotes, as in vertebrates that are busy laying eggs on land.
Yeah, so what do you think came first, Rob, the chicken or the egg?
Well, I don't know, but maybe potentially some scratches on a rock might have been what came first.
Indeed,
Right.
and that is what we're going to be talking about in this week's Fossil Files.
So, Susie, what have you been up to since we last spoke?
Um, Nothing.
Nothing, nothing
Absolutely
at all.
nothing. I've done nothing at all. What have you been up to, Rob?
Well, I've been on holiday in California with me and the kids, so that was fun.
Ooh, where did you go?
But so we took them all over the place. We saw elephant seals, turkey vultures,
Did you go to La
condors.
Brea Tar Pits?
We did not go to La Brea Tar Pits, so I introduced them to all these things and giant redwoods, but all they were excited about was a seagull that they saw steal some Doritos from a petrol station and eat the Doritos. That was their lasting memory. But all of these things, elephant seals and birds and lots of the lizards we saw, they are all amniotes. So, Susie, what do you tell us about what this week's paper is about?
That's an amazing link you did there, Rob.
Yeah, yeah,
Amazing. So this week's paper is called Earliest Amniote Tracks Recalibrate the Timeline of Tetrapod Evolution. Now, this is a paper that was published actually not very long ago, just a few weeks ago, in May 2025 in Nature. And it is by a number of authors. The first author is John Long from Flinders University in Adelaide in Australia. And then there's some Swedish and Polish paleontologists, including the senior author Per Elberg at Uppsala in
absolutely. And
Sweden.
Susie, can you remind us who the second author is?
Well, the second author on this paper is Grzegorz Niedzwiecki, who I will be
Again,
for.
I'm not going to make you do Polish names every single time. Although having said that, this is going to overlap with Poland again. Sorry about that.
It is. So I'm once again apologising to Grzegorz for the butchering of his name. Happily, there will be no further Polish pronunciations in this podcast.
Mhm.
So, as you mentioned, Rob, at the beginning, this paper describes some fossil trackways, which and this discovery pushes the origin of animals with legs, the tetrapods, and particularly sorts of tetrapods that lay eggs, the amniotes, much further back than was previously realized. So that's kind of the punchline of this paper. Okay, so we should probably discuss what a trackway is first. Rob, do you want
Mhm.
to? Have you ever found a cool trackway?
No, I rarely do field work in that sort of way. I don't do anywhere near as much field work as you, but I don't do that kind of field work at all. I also would find it quite hard to do that kind of field work because if I'm busy up and down looking at rocks, staring down for hours on end, some of these things are quite hard to identify as, as a fossil rather than just some background, bits of crack in a rock. You must have the eye to get this in.
Sometimes I think fossil trackways, after a while, every single little lump on a rock starts to look like a dinosaur footprint. It's
Mm.
terrible, and that sometimes, that I'm pretty sure they're definitely not trackways. I did find, however, a very convincing pterosaur trackway once, when I was doing field work in the States. That was pretty cool. They're really interesting because they have their forelimbs because they're actually four-legged pterosaurs. So pterosaurs are flying reptiles that lived alongside the dinosaurs, and they walked on four legs, and their forelimbs because they've got these big long wing fingers. They make this kind of funny sort of three-toed imprint, which sort of faces outwards and away, and they have this very long one finger's very long. It's very unusual print, so they're very characteristic. And I found one of those. That was super cool. But anyway, Rob,
Oh, cool.
tell us about what trackways actually are.
So, fossils, and most of the time when we think of fossils, we're thinking of bones and shells, the actual mineralized bits of tissue of anatomy left behind. But actually, trace fossils is a whole other category of things, which is sort of traces of any kind of behavior. So, trace fossils can be all sorts of different things, including some of the things we talked about last week, like a burrow or something like that. But most common trace fossils that I talked about a lot are fossil trackways, where we might see the fossil often on a flat surface, maybe some sort of mud plane, and then you'll see some footprints that have been left behind, and then maybe you'll be able to evoke some behavior. Now, they're not always footprints, sometimes they can be feeding, but these ones, for example, are the sort of classic sort of trace fossils, where we not only get some footprints, but we might actually see, look at the way that they're arranged to think about how things were walking or moving.
Yeah, absolutely. And these particular trackways have been interpreted by the authors to have been made by amniotes. So, as we said at the beginning, amniotes are vertebrates that lay an amniotic egg. So that's an egg that has like a series of membranes. And but critically, of course, has some sort of outer covering that prevents the egg from drying up. And so this was like, so it doesn't have to be laid in water. And this was like a real kind of innovation in the history, the evolution of vertebrate animals, the ability to move away from water and not have to keep coming back to water to lay your eggs. So it allowed the evolution of the amniote egg allowed animals to become fully terrestrial, right?
Mm.
And of course, it also includes us. We're amniotes, right? We don't lay eggs, but
Hmm.
mammals still have their babies surrounded in all these different membranes that are actually inside an egg. So
Yeah.
amniotes are like today they include the crocs, the birds, the mammals, um, and the squamates, the lizards and snakes, right? So it's
Yeah.
only the amphibians that have to go back to water in terms of the animals that are living on land.
Yeah.
Obviously, that evolution of amniotes was really critical, right? And
Hmm.
really affected land ecosystems. So this paper is about when that event occurred, right? When amniotes first evolved.
Hmm.
Um, and prior to the discovery of this particular trace fossil, it was generally thought that the first amniotes appeared in the fossil record about 350 million years ago in the early Carboniferous period, and that they split into two lineages. And those lineages are called the synapsids and the sauropsids. So the synapsids are the group that led to mammals today, and there's lots and lots of synapsids that are now extinct, but were along that lineage. And then there's the sauropsids. And the sauropsids are the lineage that gave rise to the reptiles and the birds today. And again, lots of extinct groups, including, of course, the dinosaurs in that. Um, and those two lineages split from each other in the late Carboniferous about 320 million years ago. So about 30 million years after the very first amniotes in the fossil record evolved.
Hmm.
Now, there's an interesting question here, isn't there, Rob, about how do we tell that something is an amniote in the fossil record?
Mm. Yeah, that's tricky. Well, first of all, before we go too far down that line, I think this paper, I guess, is difficult because it introduces lots of names of critters of things that look fairly similar to me that I get a bit lost about what sits where in which part of the tree. But actually, it turns out that's because I'm me being lost about which of those fossil critters sits in which part of the tree is actually reflective of the truth, right?
Yeah,
There's
yeah, yeah.
ongoing debate about which fossil sits in which part of the tree. So is it an amniote or not an amniote? Is it a sauropsid or not a sauropsid? We're looking at all these things that look roughly like, I don't want to say lizard because a lizard is quite an advanced kind of thing, but we're dealing with some sort
They
of
do look a bit like a
they
lizard.
do
No,
look a
no,
bit
they
lizardy.
look a bit like a lizard. Yeah.
Yeah, some sort of lizard without a neck, so some sort of stocky, sort of like Pokemon type, a child image of a sort of, a thing with a long tail and legs. And there's all these things that look like, they're fairly similar. And then do they fit or which part of the tree? Are they at the stem or the crown or the sauropsids or the synapsids or the anaspids? It's a bit messy. It's a bit murky because, there's not a lot to distinguish between them, I guess.
Well, and the critical thing, right, is that, we define an amniote by its ability to lay an amniotic egg. But unless you actually have the animal gets fossilized in the process of laying its amniotic egg, you can't,
Yeah.
so what you have to do then is you have to look at features of the anatomy that
Mm.
we think are restricted to animals that lay an amniotic egg, right? And in
Mm.
this case, it seems like there's a really critical feature, which is claws. And it
Yeah.
seems that I did not know this before I read this paper, but it turns out that claws are a feature that we see in synapsids and sauropsids, but we don't see in earlier tetrapods or earlier amniotes that lie outside of that sauropsid and synapsid lineage. And that's critical for this
Mhm.
paper, right?
Yeah, indeed.
Because
But I think I want to return to that later on because I wanted to investigate. I think we should talk about that claim a bit further on, but we'll come up with why that's important later on. So go ahead.
yeah, okay, all right then. Well, we should also talk about why we care. Why, what is it? Why does when the amniote evolve, when the first amniote evolve, really matter? Um, and it's kind of interesting because, as I said, it seems like about an hour ago now, but it was probably only about 3 minutes ago that these very first amniotes appeared 350 million years ago. Now, about 360 million years ago, there was a massive mass extinction, the end Devonian mass extinction. And this is one of the big five mass extinctions in the history of life. And so it's kind of been speculated that you have this big mass extinction and it wipes out loads of stuff. And so you've got kind of this vacant ecological space potentially for new innovation and new things to radiate into. And so there had been kind of speculation that we get this sort of radiation and this evolution and then radiation of amniotes straight after this time period, as a consequence of that mass extinction. So that's
Mhm.
going to be really important later on for this paper, right? Because
Yeah.
I think we're going to blow that out the water, aren't we?
Yeah,
Or
we
at
had we
least,
had this nice we had this nice tidy picture. The Devonian is the age of fishes. We've got all these lovely big diverse fishes, all sorts of different things, chondrichthyans and placoderms and some early things walking out on land. And then in the Carboniferous, once all that has been wiped away by the big extinction event, then we've got the diversification of the things living on land that we would recognize and be familiar with. That's the nice tidy picture that is in a textbook of, and indeed I might tell my undergraduate students because it makes life a little bit easier than this complex situation, I guess.
yeah, absolutely. But do you know what? We should actually probably talk a little bit about what the fossil is.
Yes.
Do you want to describe it?
Well, and I think that's fine. Yeah, we've been doing some context. So this is some fossils described in Australia. So I guess the age of these is quite important, but these are from Victoria. I actually looked up where they were from. I was assuming it was in the middle of nowhere in Australia, but actually it seems to be not far away from an actual town and people.
Well, I
Maybe
think the
because
thing with Australia is like you're not going to find it if it's in the middle of nowhere, are you? Because there's no towns or people. And
no,
actually,
indeed,
that's a big bias in the fossil record is that we tend to find
absolutely.
most fossils near where people and towns live. Anyway,
So
crashing on.
sorry, go ahead. And before I mention what the fossils were, I guess I was also intrigued by the fact that it was discovered by two non-professional members who are authors of the paper, which is pretty cool. So these
Yeah,
aren't
that
a
that's
professional
an interesting thing,
paleontologist.
isn't it? Yeah. And
So
I
that
mean,
was
I felt they laboured that a bit actually. They went, this is an amazing example of citizen science. So I thought, well,
yeah,
actually, this is just an amazing example of fossil collecting. Um,
yes,
but it does highlight, something that we talk about all the time, right? That
yeah,
the importance of amateur collectors,
yeah,
because we're not out there all the time. There's not very many professional paleontologists in the world, and we're certainly not
yeah.
out there all the time looking at fossils or trying to find fossils. So yeah, I think
Absolutely.
it's really
I wouldn't
important.
necessarily describe this as citizen science. Citizen science, I think, is when members of the public, do a big data collection study for you, and it's everyone, and it's a sort of education process. This is two paleontologists that aren't necessarily professional that have found a fossil and contacted some professionals and collaborated with them. I don't think that's quite the same.
No.
Um, but well done to them. So that's Craig Urey and John Eason. Congrats to them. Anyway, so I should actually describe the fossils is what you asked me to do. So we've got a slab. It's quite small. Yeah, it's not massive. It's about, I don't know, 50 centimeters across. And on it are some tiny pock marks. Now, the thing that makes you think, well, why are these fossils rather than anything in particular is because they do seem to have the rough appearance of being a footprint. Although with fossil footprints, you have to bear in mind that they don't ever look like pristine. What you're actually looking for is the interaction of an organism with a surface. So it leaves behind these sorts of marks and scrapes and distortions. So we have got some big ones, which have sort of a series of toes splayed out, like four toes, five toes, I think, in some of them. And then we've also got another set of them which are more narrow and, crucially, have long scratches at the front of them, which they have interpreted as claws. So they look like, imagine if you, classic wicked, who was the witch who had the long fingers? I don't know who that was. Do you know what I'm talking about? That's like a,
No.
no. Imagine having very, very long fingernails. Maybe you're a drag queen, I don't know. And you scrape those along some muddy surface and you've left behind these sorts of long scratches that sort of are in front of the toes.
Yeah, absolutely. And I think that there's kind of an interesting story with the slab as well, isn't there? Because they the way they've interpreted these different footprints. Of course, one of the issues that we have when we're looking at trace fossils is it's difficult to know whether if you have multiple sets of trackways, for example, footprints, sequential footprints, whether they were two animals walking side by side at the same time or whether they occurred, they could have occurred days apart, right? And here it's quite interesting because they've got one set of footprints and then it seems to have rained and there's raindrop marks. So raindrop marks are a thing that's sometimes preserved in the fossil record. It's kind of cool. You get like the evidence for where a raindrop has made a little crater when it's hit a mud. And so they've got the first set of footprints, and then they've got raindrop marks on the rock and inside the first set of footprints, and then they've got a second set of footprints without the raindrop marks inside. So it looks like it was the same sort of animal, or possibly even the same individual, walking across this area before and after a rainstorm.
That's super cool. I love the idea that you could actually get that amount of information about what was going on temporally. I mean, obviously, we have no idea how long the gap between those two things are, but it does imply that there was some sort of gap between the activity, which is nice. and also implies something about the environment in which they're living in.
Yeah, absolutely. And also that the two trackways are slightly different morphology, as you said. One's kind of more squidgy, deep imprints, and one is a more scratchy, and you can see the fingernails more. So maybe that is also related to how solid the sediment was at the time that they were walking across,
Hmm.
because that's something that you have to bear in mind quite a lot when you're working on tracks, right? That actually how squidgy the sediment is can affect what the shape of the footprint that you get out.
I didn't think of that. Actually, what you said about the rain just makes me think that. I mean, I'm always banging on about toponymy, the way these fossils are formed is important to their interpretation. But in this particular example, we have this really unusual situation where we've got one set of trackways and another set of trackways on the same slab that have different preservational situation. Because what the second animal, or maybe the second instance, was walking across sediment that would have been wetter, which may have changed the way that those trackways were formed, which is an interesting point. Maybe that leads to more scratches or less scratches. We don't know.
Indeed, and actually, our friend of the fossil files, Peter Falkingham at Liverpool
Hmm.
John Moores, works on exactly this, right? So
Yeah.
he looks at how when you put different kind of different consistencies of sediment and you put your footprints in it, how that affects the morphology of the footprint that's left over and
Yeah.
what how we interpret that.
Yeah, Peter does some great work. It's interesting because you can do all these experiments, but also I've seen him trying to get a crocodile to walk across some mud and like trying to get it get under a tunnel. And see this video of him arguing with the crocodile. You can't get it to do what you want, it seems. The crocodile wasn't prepared to just walk across some mud for the sake of science. We want to know what footprints you leave behind, crocodile. Do it.
Amazing. Okay, anyway, so that's what the fossil looks like. There are two really critical things about this fossil. And as I said earlier, the first is that it includes these claw prints. So claws, the authors argue, are only known on this sauropsid amniote lineage. So they're not known, and down the synapsid lineage, they're not known in early amniotes. So apparently the
Hmm.
first things in the fossil record that we think are amniotes, they don't have claws, and nor do amphibians, except then they give a bunch of amphibians that do have claws. But they think this is maybe a convergent evolution. Rob's
Hmm.
pulling a face, listeners,
Yeah.
that suggests that he too is skeptical about this claim. But anyway,
Okay.
apparently there's some frogs that have claws or like claw-like
Hmm.
things. I didn't know that. I don't know anything about frogs though, so why would I? So they're interpreting these as early sauropsid footprints. And just to remind you, the sauropsids, of course, are the group that went on to uh, evolve into the crocodiles and the birds and the dinosaurs and the reptiles and all of those. Now, the
Hmm.
second really critical thing about this fossil, though, is its age. So the rocks that this fossil is found in, that these trackways are found in, um, date from between about 359 and 354 million years ago. So remember at the beginning, I said that they think that this sauropsid and synapsid split was 320 million years ago. Well, here we have sauropsid footprints that are around about 359 million years old, so much older. It doesn't sound like a lot, but when you're thinking about millions of years, that's 30 million years is actually a really, really long time in evolutionary history, right?
Hmm.
So it's really quite close to the base of the Carboniferous, right after this Devonian and Devonian mass extinction.
So I wanted to ask you a question at this point. Well, first of all, that the shifting of that timescale is really important because of Roma's gap, but we'll come back to that. But I guess I wanted to ask you, as the geology person here. So I was thinking, seeing how central, like basically, the really important part of this claim, these trackways, is its morphology in the sense they've got claws. But we're going to come back to that. Second is its age. So are you? But the interpretation of its age boils down to some geology and trying to do some alignment with other rocks around the place. Well,
Oh,
anyway, let's not
interesting.
get too much head up on geology. They tell us it's the early Carboniferous. We should probably believe them. So when I say early, earliest Carboniferous, we're talking right
The
at the very,
earliest,
very
very,
beginning.
yeah,
Yeah, yeah.
yeah, yeah, yeah. So of course, what the if we take that date as the truth, and we take the fact that claws are um, unique to these sauropsid synapsid animals, and that these are indeed sauropsid footprints, then this means that we have to shift everything, the whole of the evolution, all of the evolutionary tree, we have to shift back about 30 million years.
Hmm.
So the first amniote must have evolved long before that sauropsid synapsid split. And in
Hmm.
fact, we can use molecular phylogenies and look at the number of changes that have occurred in in the genomes of these of different animals to actually try and kind of figure out how long that time period might have been. And they reckon it's around 30 million years, don't they? So, they want to push that back then, that earliest amniote, instead of evolving 350 million years ago, they want to push that down to 380 million years ago, in sort of the later part of the Devonian, in a time period called the Franian. I think you pronounce it Franian. It's spelt Frasnian, but I feel like it's
I think
pronounced
it's
Franian. Do we
Franian,
know
yeah.
that? Franian? Let's
Franian,
go
yeah.
with that. Um, and that, of course, also means that if we go then, even back further down the tree, then we've got a bunch of like really long extinct tetrapodomorph fish. So fish that are more closely related to tetrapods than they are to other fish. Um, they must have evolved in the early Devonian. So as Rob said at the beginning, the Devonian is classically the time of fish. There's loads and loads of fish around, but actually now maybe we're pushing that down, and actually the time of the fish is only the early Devonian, and by the late Devonian we've got all these tetrapods running around. And so yeah, basically it pushes everything back 30 million years.
Absolutely. I think that's the right way to frame it. I guess I was thinking about telescoping. If this event pushes things back, then everything else has to go back, as you said, like a. But I guess that is how paleontology often works, right? We find things earlier and earlier, and it keeps going back. And these guys have already done this once before. They did it with this tetrapod trackway in Devonian Poland, which is where I first came across Grigorz, and he was working with Per Olberg on that. So they found that that was important because I guess we're thinking about when things started moving out on land, and they found some trackways in Poland that were, I don't know, however many, I can't remember off the top of my head, like 10, and it was at least 10 million years, I think, earlier than any of the body fossils, the famous ones that we think of, like Ichthyostega or Tiktaalik or whatever. These trackways were turning up earlier. So there's a consistent pattern of the trackways turning up, implying some level of behavior before the body fossils turn up. And in this case, the gap is pretty big and implies that there's a big missing gap, but that's where Romer's gap comes into it. But I guess that's the main conclusion of the paper, isn't it? That everything's much more, earlier than we first thought.
It is, and what they're arguing really is that tetrapods, amniotes, didn't radiate as a diversity, didn't diversify as a result of the end Devonian mass extinction. In fact, they were already widespread and diverse by
Hmm.
that time. And maybe it was only the sauropsids and the synapsids that were then radiating after that mass extinction. So
Yeah.
it sort of changed that picture of what the implications of that mass extinction. I think I really, really like the last line in this paper, because it's something that I feel very passionately about, and it
Hmm.
doesn't get said enough. It says here, so they're talking about, they say, against this background, two things stand out. First, that the interpretation of such a fossil record is critically dependent on the phylogenetic inferences and cannot be read as a literal account of the history of a group. We can leave that one. That wasn't what the thing I love. But the second, the fundamental continuing importance of paleontological fieldwork as a source of new knowledge. And, I think that's really important, because that is the thing, collecting and discovery is, it is the most foundational thing in our discipline. Without fossils, without the new fossils, without new data, we can't reinterpret what we thought we knew. We need to be reinterpreting the light of new data all the time. And you're talking, you've said several times in this podcast Romer's gap. Hopefully you're going to talk about Romer's gap now, and you can tell
Yeah, I
us
need
what
to
that
explain what
that
that is. I
is.
guess really, I'm not sure it's a groundbreaking conclusion though that paleontology requires new discoveries, right? I don't think anyone's suggesting that's not the case. I mean, I guess
Well,
we'll have to remember that next time we put in a grant application, can I just go and find some stuff? It's very hard to get a grant application to say, can I
it's
go and dig some
virtually
stuff out of the
impossible,
ground?
right?
Yeah,
Yeah,
yeah.
it's incredibly difficult to convince funders that this is the thing that we need to be doing. So
And indeed, in these guys, they didn't do that, right? They didn't say, can we have a grant from the Australian National Academy or whatever it is called to go and dig up these things? Some people found some and sent and got in contact with the right people, and then they worked together on it, which is also another way to do it. Bring your non-professional paleontologists into the fold, I guess, is another way of looking at it. Okay, so there were two things I wanted to talk about though. So that was one was the phylogenetic differences, and second was the Romer's gap. But maybe we should talk about Romer's gap first of all, because we've talked about that like 6 or 7 times. So this is at the very beginning of the Carboniferous. We've got this like 15 million year gap after the mass extinction in the Devonian, where we don't see an awful lot of fossils. So it's always been well known that that particular point in the geological history of life on Earth was a problem, because there are various different reasons have been put forward for that mega bias, but it's 15 million years is a big time to not get an awful lot. So it's named after Romer, the famous American paleontologist. I can't remember his first name. Alfred?
Alfred Sherwood.
There you
Yes.
go. There you go. So he first identified this. So that's interesting, I guess, because when you do something like this and you shift everything down a bit, then that implies that, I guess there was already a quantitative expectation that there's a missing record going on. We have this idea that there's something missing. What's going on? That makes sense. But oh, my brain's just stopped. What was I going to say?
I really hope you leave that in. Don't edit that out.
So Roman's gap is an interesting one because we've got all this gap, and then for example, this one is sort of close to that, but actually that is being chipped away. There are teams of people that have identified the right places in time and the right places in the world to go. And the Scottish borders, as Jenny Clack before she died, has been up there working with a number of different people, finding all sorts of tiny little interesting reptilian-like critters, in this time, and it is being slowly filled in. These big biases can be filled in if you slowly chip away at it and know where to look and do some wise field work.
Yeah, absolutely. And actually, um, I think that it's incredibly clever calling it Romer's Gap, because this by naming a time in the fossil record where we haven't got very many fossils, you instantly make it a thing that we need to fill and solve somewhat, and thereby all your grant applications get written. So what I was going to propose while you were having a little think there, Rob, was can we come up with like a Sansom's cleft or something in the fossil record that needs to be solved, right?
Sansom
It could
Cleft, very hairy, needs more fossils in it. Yeah.
exactly, but
Uh,
then we can write grant applications and say like, what I need to do. There's this critical time period known as
yeah.
Samson's cleft that
I
we need
did
to
do that in
solve.
yeah, in one of my earlier papers on fossil fish, I did talk about Talima's gap, who is she's a Baltic scientist who worked in Russia and other places. She identified a gap somewhere in the Devonian. I can't it's been so long that I think about it, but I was quite happy using the phrase Talima's gap in that because she had that I'm not going to call it after myself, but she had that prospect of being called that particular person with many years of patiently navigating it. But I haven't ever put in an application saying, can we fill in Talima's gap? Not,
Well,
not,
there you
not,
go.
not appropriate. No.
So I think that's how you know as a paleontologist that you have made
Yeah.
it is
Yeah.
when you have some sort of gap named after you.
Or name some sort of problem or error after you.
Yeah.
What can I name? What do you want to be named? What can I? I think we have to. You can't do it for yourself, so I have to name something after you, and you have to name something after me.
Okay. Well, let's come up with something. It could be something like a really niche anatomical feature.
Well, you've always been slightly frustrated about the Thagomizer. Should I instead call it the Maidman at the end of the Stegosaur tail? That seems like you're the right person to call that.
Maidment spike.
Yeah, the Maidman spike or the Maid Mentor. I don't know. Anyway,
Anyway, we were talking about
we're
Roman's Gap.
Paramigos there. So that was the gap, I guess, is that give it a name, fill it in, and be wise about where to do the field work to do it. Because, the way that you deal with these problems is careful consideration of where the right kind of rocks and the right kind of place in the world are to get that solved, I guess.
Yeah, absolutely. Yeah.
But the second thing I wanted to ask about was this phylogenetic inference, because that's what this boils down to, right? And I keep going on about this, and we never actually dealt with it. So maybe we should have talked about this earlier, was the clause. This all boils down to the presence of the claws, right? The morphology of, well, not all. There are some other things as you talked about with the shape of them and with the width and the height. But the main fact is it's got claws, and that was what we are saying. It means it's an amnio. It fits somewhere in the proper amnio. It's big grown-up amnio. It's not early amniotes because that's what they have claws. But I'm not an expert on this area, but I want to be a bit more convinced about this because they give a long list of things that have claws that are not amniotes, which I found a bit tricky. So there's temnospondylus, which are stem amphibians,
Amphibians.
if I remember correctly. And then the microsaurs. The microsaurs was the one that led me down a bit of a dark hole when I read this paper. So microsaurs I've come across occasionally. When I was thinking of describing these Pokemon looking things, that's what I was thinking about. These sorts of first draft of a reptile. This sort of like if you draw it on paper, some of them are quite long and thin and fantastical looking with massive teeth. But there's loads of microsaurs, right, from the Permian and the Carboniferous. They're really lots of really nice fine preserved ones from the Mazon Creek, which is an exceptional preservation site. Now, I was trying to figure this out. They described them as having claws, and Not all of them do. Some of them do. This is the difficulty. Claws isn't a very stable phylogenetic characteristic, right? It converges. It's lost. It's going to depend a lot on your ecology. Are you a burrower? Are you a tree climber? These are things that are very central to being an amniote or living on land. You may lose or gain your claws as you wish. So maybe you could be an amphibian and have one, or maybe you could be an early amniote and have one, or maybe you could be a microsaur and have one. Now they cite a paper where the microsaurs were sorted out as potentially belonging within the amniotes and being proper amniotes, but there's been a paper since then by Robert Rees, mm, faces about I don't know if we have to edit that out. About implying that actually that's not solved, right? There isn't widespread agreement about whether microsaurs fit. Indeed, they could be on the amphibian lineage. So, if claws exist elsewhere, that's what I think it boils down to a question about phylogeny, as is always the case, because that's what I'm always going to say.
Well,
If
it's a
if
good
the
point. It's a good
Yeah,
point, Rob, because also the authors, go to quite some extent, quite some effort in this paper, pointing out that trackways are really, really important because what they do is they tell us about animals for which we do not have a body fossil record. So, we have absolutely no idea what these animals are fundamentally. So yeah, they could, they have got like these sort of little human baby hand type footprints, but we don't know anything about this track maker at all, and it could very, very well be convergent evolution that has resulted in these little chubby fingered, chubby palmed trackways
mhm.
with little claws. So yeah, I mean, without having more evidence from the body fossil record, I actually think the track record is a little bit ambiguous.
If it is an amphibian, then a lot of the central claims and importance of this paper immediately go. Like that whole pushing things and telescoping things just stops. Right? If it's a STEM amphibian, then everything's back to where it should be in terms of the timeline.
Yes, that is true. I mean, it does all hinge on the interpretation of this fossil, but then almost everything that we do hinges on interpretations of fossils. So,
Yep.
I mean, you know,
And the arrogance of me to think that I might know more than the experts and peer reviewers. I should just watch my mouth. But this podcast will be over pretty quickly if we just went, and these people have said this. That was the end of that.
well, I quite like this paper. I quite enjoyed it.
Good.
I thought it was quite good. Um, like a nature paper because it's nice and brief.
Yeah.
That's a major plus. So yeah, I enjoyed it.
I think it's got a nice message in it too, isn't it? That lots of new discoveries to be found. There's a bit, they use the word serendipity. I don't like the word serendipity, but there is, some element of chance to be found here, and work with your local non-professional paleontologists who might be out there finding things that you haven't thought about.
Yep, all good messages.
Yeah. Okay. Well, thanks, Susie, for telling me all about the origins of amniotes and where we came from. I guess that's the other thing we didn't actually mention is that this is where we came from, right? These are our ancestors many, many, many millions of years ago.
Fairly distant, but yes.
Fairly distant. Cousin first removed, all that sort of business. Next week, Susie, will you allow me to talk to you about Neanderthals, or is that because you described the dire wolves as topsoil? Is that going to be allowed?
How the Neanderthals are probably further back in time than the direwolves, aren't they? I think
I
well, they're
don't
still
think
all
so.
over burden, but
They're still
that's
over,
okay. Let's
yeah.
do that. I think it's interesting. It's interesting.
Just chipping away. Well, actually, I should explain. I can segue this into this one because one of the main messages from this one was about fossil collecting, about how to do it and who's doing it. And the question was a little, teaser was, did Neanderthals go around collecting fossils? So we're going
Oh
to find out.
yes.
Yeah. So I
Yes.
will.
Oh yes, let's do that paper. That sounds fun.
Okay.
Okay.
So it's a meta paper about what it is to collect paleontology and who are the fossils collecting fossils themselves. There we go. We'll talk about that next time.
Okay. Sounds great. I'll be here.
Okay. Cool. All right. Thanks, Susie. See you soon.
Bye.
The Fossil Files was presented by Robert Sansom and Susanna Maidment. You can find more information, including links to the original papers that were discussed, at fossils.libsyn.com, and you can contact us at fossilfiles.pod@gmail.com.